Welcome back, everybody. Is the mic okay? Great. So, for the second lecture, continuing with non-equilibrium calorimetry, we were last Tuesday more or less giving examples and general introductions of models, some mathematics about time reversal, etc. Today, we would like to enter more specifically into the subject of non-equilibrium calorimetry. As I recall, the stop last time was a bit abrupt, maybe, so I will come back to that model. But let me start again by somehow sketching the problem of the topic that we would like to address. And let me do that by drawings, actually, just to keep in mind what systems we are discussing. So suppose I have a piece of copper, I can do calorimetric measurements with that and determine the heat capacity. And basically, if I have a good piece of copper, I put it in a bath of water, for example. I mean, this is the most elementary thing. And I see what is the energy flow. I mean, things like related to how the temperature of the copper bar will get equal to the temperature of the water. These kind of things I'm doing. Okay, let us forget that a little bit in the following sense, that now I am thinking about this piece of copper and I am thinking of it as a resistor. So I'm taking it in as a resistor in an electric circuit, and the whole copper bar with the resistor is immersed in a heat bath at certain temperature T. That is the typical setup that you're using to warm water to make tea or so, right? So you're sending the battery is doing work on the system. It sends a current through electrons in motion, and this resistor will get Joule heating, and this Joule heating will medium sample of the water, and if there's good diffusing properties, it kind of makes the water homogeneously at a higher temperature, for example. But now let us take some more drastic point of view, in the sense that I really think of this as like going tiny, and the heat bath may be going very big, so that there would be no temperature change really in the bath. But nevertheless, there will be Joule heating. Right? So there is Joule heating, there is power which is dissipated in the environment, but I keep it at a uniform temperature, at least within certain scales of time and etc. Okay, now I can ask the question, these Joule heating properties, in what sense is this heat flux, so heat is over the surface going through the water, in what sense is that heat flux changing if I change the temperature of the water? But not only that, in fact, there are other properties. There could be material properties, part of this, what I call copper, but other parameters could be there in my experimental status. And in general, I will call these material properties in general lambda, and the first one would be the inverse temperature, and then there would be other parameters. And the question is, what happens to the heat flux when I change this lambda to a new value? And in a way, I'm therefore doing a thermal response theory. For the moment, no formulas, but just words that I'm asking. I change parameters. For example, I change temperature or other things. I keep other things fixed. And I'm asking, how does the Joule heating, the flux is changing with these parameters? And you can wonder indeed now whether the fact that I have a current through that copper would change the heat capacity, well, would change the properties of that heat, if there is a current or not a current. That's the question. Another thing you can imagine is that you have a typical like chemical reservoir, and say you can maybe even imagine your favorite chemical transport process. It can be about chemical or so. Think about the pores that are through the membrane in the cell. So you have different chemical potentials perhaps at the edges of a particular channel. So let me denote them by a mu1 and a mu2. But I can still be in the same watery environment And I can still imagine that I have here a large temperature bath around me. And just what is mattering for the entrance of these particles, they are a difficult potential, but you know, the usual fugacity, also the temperatures will enter, right? And so you can now imagine if I have, okay, so here also there will be dissipation. There will be dissipation. There will be a current, chemical or particle current will happen. And you can again ask, in what sense does this non-equilibrium feature of, well, we do not call it Joule heating now, but like dissipation, particles are being put in the maybe lower chemical potential, but in what sense do these properties change if I change parameters? And moreover, I can also ask, maybe for my body it is not a very nice experience, but I can also ask whether I can learn something about the mechanisms and the kinetics if I lower the temperature. If I do this experiment at low temperature, because we know from our experience in equilibrium statistical mechanics, in fact, that we reveal via calorimetry, we reveal via low temperature somehow a lot of the spectroscope of the electronic structure, the occupation levels, etc. So we can ask whether that is also true. Okay, I'm not going to exaggerate with my drawings, but clearly you can make your own invention. I mean, last time I think we had a particle which could be invented, could be imagined, maybe it's a molecular motor, I don't know, or some more mesoscopic particle, which is either living in such a potential or maybe in such a potential or maybe in a more flat potential. So the spring constant may change or the potential as a whole may change. But nevertheless, I am again maybe in the same watery temperature environment as before, and that fact that I'm changing this potential, that you have a flashing potential, maybe it's a ratchet, I don't know what, is doing work on the particle, but nevertheless I am in a stationary environment, so I'm stationary but non-equilibrium, and this work that I'm doing on the particle is instantaneously transformed into heat, so that I have a stationary condition. I mean, this is the same thing as here. Well, this work is kind of instantaneously transformed into the Joule heating. Right? There are all kinds of processes that do not concern me in the mesoscopic description that I have for the moment. I'm using what is called the condition of local detail balance in my model to get some of the principles of physics right. So these are the most. One remark I want to make here is that, well, it's a remark I have already made, is that we will speak about this we will speak about these heat processes and this heat capacity also for small systems. By nature, in steady non-equilibrium, you are already an open system. Steady non-equilibrium, you have to be driven, you have to be active via mechanisms, fuel, non-conservative forces, boundaries with particular chemical reservoirs. You are open. But you can be small. And what is big and what is in equilibrium is this heat bath here. This temperature is fixed as the temperature of the equilibrium. Now, these pictures are still relatively simple, I hope you understand, or you see, because I can imagine that your favorite non-equilibrium system has not one thermal reservoir, but plenty of thermal reservoirs at different temperatures. Or, okay, you have levels of hierarchies of non-equilibria, which are interconnected. All that is not, let's say, a problem of conceptual or further conceptual difficulty, but rather of modeling and more notation. So I will stick in the models and in the treatment I'm giving for the moment to this. But let it be said that, in fact, heat capacities can also be a matrix where you're looking at various flows of heat to various temperatures depending on what temperature, for example, in another reservoir you have changed. Right. So now allow me to counter these vague descriptions and pictures with some formulas, so to get a precise statement of what I mean by heat capacity, and in particular, what is the heat involved. So before I do that, let me say what I want to get at mathematically. And that is, again, maybe an intuitive picture that can be useful. And it is the following. So I've been speaking about this Joule heating, which is this dissipated power and all that. But suppose we make this kind of caricature of what we are doing. We are taking here the time, and we are putting here this this power set, this dissipated power of our non-equilibrium system. And suppose that we have something with time 0, and that before that time we were having a certain dissipated power at a certain level. It's a non-equilibrium system. So there is, before we change lambda to lambda plus d lambda, there is a certain dissipated power, constant, stationary. But all the time there is, of course, dynamics, and there is entropy production, and there is this. So suppose that at time 0, we actually do the switch from lambda to lambda plus d lambda. For example, we change the temperature. Maybe other things. So we do the switch from, okay, let me take here, just to be specific, let me take that we switch temperature to T plus dt at time 0. Well, you may expect and hope, or maybe not so, but let's assume that after a sufficient long time, which is some type of a relaxation time towards a new non-equilibrium steady condition, that we have a new steady condition with a new dissipated power, which is again constant. I'm making a bit of a cartoon and approximation, but that is the idea. Then we must have some relaxation from one to the other. I'm just drawing a line connecting the two. But what is certainly true is that the integral under the curve, since it is a power dissipated heat, the integral is a heat. Right? The integral over time of a power is a heat. So what we will be especially interested in is the power here under this transient part, which will be proportional to dt, and the constant here, which is, or the factor which negotiates between that surface and the dt, that is called the heat capacity. Again, do not take this literally as it is, but it gives you already the idea that what you're really doing is an old, very old theme in thermodynamics, except that instead of moving or studying transformations between equilibrium conditions, you're studying transformations between non-equilibrium conditions. It's a very natural idea, no? I mean, you're in a certain non-equilibrium condition, and you change parameters, external parameters or internal even, and you go to a new non-equilibrium condition. And this relaxation, just like for equilibrium, goes with extra, we call it excess heat. So that area here is excess heat. That's what we call heat. And for people who know these things, sometimes the stationary power or the stationary heat, I must say, it's called the housekeeping heat. So this is like the Joule heating. It's all the time. You keep your house warm, right? It's, you have your heating being burning the coal or the electricity, I don't know what. You have the housekeeping heat all the time. But then something happens in the house, and you change the parameters, maybe you open the window or something else, and you go to a new housekeeping heat, but there is a transient time, and what is extra into the housekeeping heat, that's what we call the excess heat. So this is the excess heat, and we will denote it by delta Q, even though that is perhaps a bit confusing, because delta Q is, of course, also usually since Clausius time the letter we use for heat. Okay, but it is an excess heat. So in equilibrium, you just have the same picture really, except that these powers in the beginning and at the end are at 0. But you have a certain heat which is produced in the relaxation. So it's about relaxation between non-equilibrium conditions, and if the change is a little change in temperature, you have an excess heat, and that is measured depending on the material, depending on the non-equilibrium conditions. In fact, you will have an excess heat. And that's the intuitive picture, and I would like to add a bit of formulas to that. But is there a question already here? Not immediately, perhaps. All right. So let me take this formula actually, so that I'm not making any errors. Right. So as I was saying, we have this lambda which summarizes our parameters. In thermodynamic course, you are used to that as well. No, there are things like volume or so, also the temperature, but there are other parameters that you can have in mind. And what you should keep in mind is that we have a kind of quasi, well, pseudo, whatever, thermodynamic surface, and we will make a path from some initial lambda to a final lambda on this parameter space. So we have in this parameter space a trajectory. Now, corresponding to that trajectory, we have to say, of course, how do we do that? I mean, this is a path in this trajectory space, but there is more to a path than the location of the points. There is something that enters, and that is the rate of change. So, as in usual, your textbooks of quasi-thermodynamics, but usual thermodynamics, you have the notion of a quasi-static transformation. Sometimes, in a way which is a bit confusing, people use adiabatic transformation or reversible transformation. That's fine, but allow me to use the word quasi-static because it's exactly what it's exactly in the word what I want to do. Namely, the rate of change will go to 0. So, in other words, I will have a trajectory, I will have these parameters. This curve will be parameterized by an epsilon, and I will take a protocol, it is called, where the rate of change is proportional to this epsilon. Epsilon is just a positive number, and epsilon will soon go to 0. It is the rate of change, the speed at which I'm taking these things to go. Okay, now, since I have that time-dependent protocol, I can, of course, not have a specific, strictly stationary condition because things are changing. Right? So I have to solve, so to speak, the equations of motion for a time-dependent parameter. Okay. So what I mean is the following, that I have that the statistics of my non-equilibrium system, the conditions, the probability of the condition, the density or the probability density, is a function of time and also depends on epsilon. So this will be the solution of a time-dependent master equation, a time-dependent Fokker-Planck equation, things like that. So again, I repeat, I am on a certain coarse grained level of description where I take for X something like a density profile, perhaps, but it can be much more discrete. It could be a particular molecule which has a chemomechanical configuration, which is maybe 5 different possibilities. But at any rate, I have this. I assume that I have a first-order differential equation of some type where I can solve. Let me put it like that, where I can solve, in principle at least, where I can solve for the stationary distribution. And this is usually written also out in the following sense. I have my generator, which now depends, of course, on my protocol. And here I will make this cross. That's really standing for what is called the forward generator, but don't take too much attention to that. It's working on the rho epsilon. Okay, I'm not going to write all these equations, but you should just remember that this generator is a matrix. This rho is a row vector in the simplest case of discrete state space. And this matrix is just simply is just characterized by transition rates. And these transition rates are telling me what is the probability per unit time to go from state Z to Z prime. But the transition rate itself is a function of time. And how it is a function of time? Well, through that vector, which collects all the possible parameters, and it changes at a certain rate. So that is the input. How my dynamics has transition rates, but which change in time. So I have no in general, if this is a non-trivial function in time, then of course there is no stationary solution. It's not that this will be stationary, but there is a time-dependent solution. This is nothing to do as such with non-equilibrium. You can, the same thing is true for equilibrium processes. This is in quantum mechanics. I mean, this is a theme that you have to do. Now, let me add one more piece of notation, which is, in my experience, sometimes confusing. I will now use another piece, which is rho S, and S stands for stationary. Now we are really stationary, so you wonder, just said there is nothing stationary, but this one will be stationary. And the stationary, okay, will be for a certain parameter, which is exactly the value of lambda at time epsilon t. So here is little 30 seconds. We must wonder whether we understand that notation. So by that I mean that for a given lambda, so if you give me a lambda, I assume there is this stationary rho as lambda for a given lambda, which is the solution of the equation actually. L dagger lambda is equal to 0. That's the stationary master or stationary Fokker-Planck or stationary Smolyakovsky equation, what you want, that I have been solving. And for this parameter lambda, the k have a fixed lambda. And there is a stationary probability distribution, stationary statistics, which I denote by rho s lambda. But now I can take this lambda to be changing with time. I mean, it's not that the dynamics is changing in time. I just have a one-parameter family of stationary distributions for the different lambdas. So in other words, for every lambda along that path, there is a certain stationary one. They are called like the instantaneous stationary ones, right? So of course, this is changing in time, but there is an instantaneous stationary one. This is what is called the quasi-static approximation. Yes, please.
So this L operator could be a Leuven's type.
No, no. I mean, of course, you can imagine that underlying everywhere here there is a Hamiltonian formulation, and I have a Liouville operator. This is not the level on which I'm working. I'm working on a mesoscopic level where I have operators which correspond to Fokker-Planck, Smolyakovsky, master type equation, if you wish, Lindblad type equations, but this is not a Liouville equation, it's a dissipative operator in general.
No, maybe you could take Leuven kind of thing. So then L would be a dissipative operator.
Yes, I'm already, so the temperature is also sitting in there, the action of the reservoir is sitting in there. You know, I'm not discussing that, but there are all kinds of modeling techniques to get a useful physically relevant operator here, which is a bit like what I had on Tuesday, right? Where you use local detailed balance and all that. And think about just that I have a description in the level of a Fermi-Dirac, whatever, a Markov jump process. To have it in something very specific in mind. But it's not Leuven. Other questions, perhaps? Okay, so we are over the hurdle of the notation, I hope. So this is like the instantaneous one, but clearly the solution of that equation is not this one, because just imagine that you're starting here and you're happily maybe stationary at an initial position, and then you're going to the next. I mean, the lambda is changing a bit. It takes time before you relax to the corresponding stationary distribution, but before you're able to relax, the lambda is already moving to another thing. So there is always like a relaxation and a delay. You always have to catch up. So what I'm interested in is, in fact, as you can understand here, I'm interested in time-integrated differences. But if I'm interested in time-integrated differences, then I have to understand to linear order what is the difference between that one and that one. Let me repeat that point. So I have a time 0 to a time tau maybe originally, but now I'm going to take this as a very long time. I'm going to rescale it also. So I'm looking at the time interval, which on the level of my change of my parameters, it has a, you know, if I let epsilon go to 0, that is my ID, I will have to wait an infinite number of time before I can change something, right? Otherwise, nothing will change. So there is the epsilon going to 0 and the time going to infinity. And what I'm interested in is not only in the difference between this and that, they go to 0 by the way, right? So the limit of epsilon going to 0 of that one is that. But I'm interested in the linear order correction to the quasi-static approximation. These words making sense, so I repeat them. I'm interested in the linear order in epsilon approximation, the linear order correction between the solution, the real probability, and the approximate quasi-static solution. And what do I have to do with my time integration? Well, I have to do the following. So now I'm going to like basic formula. So I want to look at a excess heat. So let me write it as a Q epsilon. And as I said, it will be an integral in time. And it will be running from 0 to tau over epsilon lifetime. And there will be a difference. And a difference of what? Well, I said of what? In the sense of power, right? What is power? And so let me first make the notation and then explain it, or let me first write it. So there will be here a P lambda. That's my first thing. I'm sorry, this sounds a bit complicated, or looks a bit complicated, but that is just the following. Remember that I hope to have in my hands a function, which like P lambda of x simply. I hope to have in my hands a function that for every lambda tells me if I am in condition x, what do you expect is your power that you dissipate. That I hope to have in my hands for my model. I have to get from my model to a function, which means the expected dissipation power for parameter lambda when my condition is x. If I have that, then I can look, well, actually, let me make it less complicated, this notation. I think I can make it less complicated, excuse me. This sounds too complicated, all these brackets and epsilons. So let me repeat it. I repeat Q epsilon. I have an integral, that doesn't change. Now, I have this function. I evaluate it at time epsilon t. I have it in x. And here I take it, I do it as if it is a discrete state space, just to make sure. And I evaluate this expectation in the instantaneous probability. So this is the expectation of my dissipated power, which we do not know yet too well, but I suppose that exists at time t because I'm looking at my statistics at time t. And I'm subtracting from that the same thing, but for my stationary value. Voila. That's what I'm doing. That's what I call excess heat. So you see, here I'm looking at my, if I take this times that, remember this is the S here, this is the S of stationary. So this is like the stationary heat flux. The stationary heat, and then integrated over time, it will be like the like heat. Stationary power, expected power, right? But when I am in stationary for the lambda epsilon t, so I'm taking here the instantaneous value as if I am stationary, and the difference is here that this is the true solution.
So the stationary state is for every instant.
Sorry, say it again.
The stationary state is for every instant.
Yeah. So for every instant, I repeat, remember that notation, right? For every instant, I have for every lambda, I should say, I have a stationary distribution. But of course, I can now, over the path, look at all these lambda in the path, and I just plug them in as a function of time. And I look at the difference with the true distribution. And the expectation is always of something that I have not specified yet, which is the power dissipated in condition X. Linear, well, I first have to, that's the definition. Is there a confusion here? Or is
I was thinking sum over x, that is like the sum over all possible trajectories from lambda to lambda?
No, this X is just the states, so these are just the states in my non-equilibrium system. So the configuration space actually. Just the configuration, not the trajectories. I'm not, so the only thing which is changing is there is a trajectory of lambda, but here is just, I have the state of the systems is not changing. The possible states of the system are not changing in time, right? I always have the same system. Okay, so I have not said what is the P, but the interpretation should be the dissipated power when you are in condition X. So I have to make sense of that, and that will come. But for the moment, think of this as a general function in the mathematical sense. I just want to stress, okay, what I'm doing is something like I'm doing here, except more carefully. Because here I went from t to t plus dt, which is like a trajectory, right? But okay, this has a meaning, but not much of a meaning mathematically. And I stress that I mean, why am I stressing that? Not so much for the mathematics, but just that it connects with the formalism, which is just the same as in equilibrium. It's quasi-static transformations. That's important. And there is a reason why it is important, and the reason will be very clear in a moment, and it is the following. So here is the first, well, let's say, mathematical result. Oh, I should not use too much. But here is important. That is that even without specifying the p lambda, I have the following result. So that's a little lemma or theorem that the limit of epsilon going to 0 of this q epsilon is an integral over my curve that I may be calling gamma. It's a curve in parameter space. It's a vector. So this is the vector of all the parameters. There can be a scalar also. Of what? Of the stationary expectation. So the brackets here is a stationary expectation at a fixed lambda of nabla lambda of a function v, where depends on lambda, and we call it a quasi-potential, and it is defined as, and these are many things at the same time I'm putting on your plate here. Okay, so let us try to explain that. It will hopefully pay off that we have all this notation. I think it will be useful. First of all, don't look at v lambda. I'm just saying that v lambda is a state function. So it depends on, it's a function of x of the non-equilibrium condition in the sense of where are you in the state space of the configuration of your system, right? Where is the molecular motor or things like that? Or where are the particles in your system, something like that. So v lambda is a function on just the states. It depends on the lambda, which is the parameters that I have. It depends on temperature and all what you have. Okay. Now, this nabla of lambda is just taking the derivative of lambda. This bracket is just taking the expectation in the stationary distribution with lambda. Stationary expectation, this is done with what we call rho s lambda, the solution of the backward or the forward homologue equation, the stationary distribution. Now, before we go on, you should be, or you could be, let me not say you should, but you could be already a bit happy about this formula. The reason being, this is what we call a geometric formula. It only depends on the trajectory location, so it's really a curve in parameter space. I'm not sure whether you have heard about things like Carey phase, but that is the thing that you are going to, right? So you have this thermodynamic space of parameters, and if I take now a curve which is going to be a loop, for example, I can use things like Stokes theorem or what have you, and understand this formula also in terms of an area in thermodynamic space, and it will be purely in terms of the parameters, so purely in terms of the geometry. So in particular, what I mean by geometric is that this formula is invariant under a transformation where I go where I rescale the time, so to speak, in my parameter space. It's a geometric formula. And moreover, you see, if I change lambda to minus lambda, it changes the sign. It's a
So
geometry.
non-equilibrium phase space remains fixed, right?
The phase space remains fixed. This is the state x or element of that. The lambda is the term, is the parameter space.
So the way that it traverses the phase space, that is decided by that.
No, lambda is the thermodynamic space, right? So here we have the lambda space, and part of this lambda space is temperature, but also other parameters like switching parameters, potential parameters, what have you. And this expectation takes the expectation within the non-equilibrium stationary distribution. Okay? Yes, please.
No, I think I missed it. So this is Q is the excess heat.
Yeah, that's what we call the excess heat, and I'm
okay,
saying
fine.
that the excess heat and the limit becomes a geometric quantity and is determined by a potential V, we call the quasi-potential in this way. And this quasi-potential is in fact something that you perhaps remember could be associated to the drawing I made. Because here I'm looking at an x, this is a function of x, and I look at time t, how this power, the expectation at time t for a fixed lambda, and I subtract the stationary power. We will do it. Why don't we do it in equilibrium and see what happens? Maybe we do it in equilibrium.
No, sorry, I believe epsilon tending to 0 should be 0, no? But
What is
because
the difference?
Difference.
Yeah, right, but you integrate from 1 over epsilon. So the difference is order epsilon.
No, well, physically, I mean, at each instant, you are at quasi.
Yeah, so this goes to there.
I see.
But it's not exactly true. It goes like epsilon. Okay? And as you integrate over 1 epsilon, you get something finite. And this thing which is finite is exactly that thing. Is that okay? More questions? I'm sorry for the notation here.
So you are saying that the VW is a state variable.
Who is what?
VW is the first one.
The quasi-lambda is quasi-potential is a state variable in the sense that it is a function of the state of my non-equilibrium system. Exactly. Of course, it is also parameterized by the lambda. Let's do the simple equilibrium just to make it specific, maybe. Yeah. Yes, please.
So the integral is over like all possible
No.
answers.
No, one part. Yes. So, by the way, what I will define as heat capacity, let me immediately add it. So the heat capacity will depend on the lambda, but what will it be? It will just be this. So in general, for a d lambda, so if I take the derivative of q with respect to lambda, so to speak, well, here it is. So in particular, if I look at the heat capacity where everything is fixed, but lambda is the temperature, then I will have that this is the derivative with respect to temperature of this V lambda associated to the stationary state for a given lambda, which is a fixed temperature. Lambda is temperature and all the rest, except that I allow me now to add a minus sign. Why? Because the convention is that heat capacity is related to the flux into the system. Well, this is the flux outside the system toward the lambda. So just this silly minus sign that enters there. So, but let's see what happens in equilibrium. So to make sure we understand at least the equilibrium.
Sorry, please.
Yes, please.
So in quantum mechanical analogy,
Yes.
so I think somewhat related to Berry phase. I mean, the wave function picks up the phase.
Yes.
So I mean, you could have integrated without power also. I mean, you see.
Because for the moment the p is a function, right? I didn't say what it
so
was.
if you set p equal to 1, so
Yes,
that would be
that-
exactly the Berry phase.
No, if I set p equal to 1, it's 0, right? Because it's normalized. The sum over x is 1. You cannot literally put p equal to 1.
No. So okay, maybe we come back.
Yes. Let's see what happens in equilibrium, perhaps. All right. So, well, in that, if I go to equilibrium, of course, I have to tell you what I will have in mind for my power. Right? So, let me open here this little window. So let me immediately say, for at least for Markov jump processes, which is the easiest case for our notation, the p lambda x will be exactly the following. So I look at all the possible transitions that I have from x to y. They go with a certain rate, and I have a q which will depend, which also depends on the transition from X to Y. That is the heat, which is defined via the condition of local detail balance to be the ratio of these things as we had it last time. So, okay. So before I go to equilibrium, so in equilibrium, what do you have? In equilibrium, can I use blue, you think, or would it be disastrous to use blue? I mean, maybe the people online can complain if they do not see it, or maybe you can check whether you see it. But so in equilibrium, is it readable?
Yes.
So in equilibrium, you have that this ratio satisfies global detail balance. Yes.
So this thing is outside the system.
Yeah, in this notation, I put the Q alpha xy is the heat towards the environment. Towards the environment. Yeah, you know, there's always this misery of towards and inwards and all that. If I would have been clever, I would immediately have started with inward and then I wouldn't have to do the minus sign. So when we are getting the equilibrium, then we know that this is the ratio is given by the logarithm of the ratio is, as usual, the entropy flux, but in equilibrium, it is just the difference of a potential, right? So in that case, the equilibrium situation is when this is equal to Ex minus, so let me put Ux minus Uy. I'm forgetting now the notation with alpha, but also in equilibrium, the potential can depend on parameters, but let me not write it. Right, so in equilibrium, is it okay? So there exists a potential in equilibrium so that this is true. And you recognize this as the heat towards the environment because the energy is changing. If I go from Y to X, the energy is changing Uy minus Ux in the system, hence Ux minus Ui in the environment. Right? So that is why. All right, so if I take here for the Q alpha Ux minus Ui in equilibrium, so this is the equilibrium. In equilibrium, I will have P equilibrium of X. I'm forgetting, so it depends on temperature or inverse temperature, the beta. What do I have? Well, look, I have the rate of change, and then I have the difference of energy. Right? But what is that? Well, it is in fact something like the elementary change in energy per unit time. I hate to write it, but it is in fact minus the forward generator acting on you. But if you don't like it, don't take it. So this is just a forward generator acting on you with the minus. Because it's kxy, ux minus uy. But it's the elementary change in energy, basically. Okay, per unit time. Now, I have to plug that in. To get the V, I have to plug that in here. But no, I'm not sure whether you will appreciate that, but this thing here I can write in an algebraic notation as an integral from 0 to infinity of what I had last week, last Tuesday, using my generator L on the function P lambda minus its average. Remember that we had the discrete time Markov chains where we had a stochastic matrix that we had to do some power. But in the same thing, if I want to know something at time t, I just take the semi group and I act on this function. Why am I writing it? Why am I writing it like that? Because this thing here leads immediately to an interpretation of V lambda as what? Well, you integrate over time e to the power t L lambda. So what do you get? You get, as usual for integration of an exponential, something which looks innocent but is dangerous. Let me write it. Sometimes innocent things can be dangerous. You get here minus 1 over L lambda P lambda. Isn't it? Well, to be sure, I have to subtract the stationary values. I just do the integration from 0 to infinity of e to the L, so that I get a 1 over L down. I get a minus. Okay, so for the moment, I think some of you perhaps may raise their eyebrows and say, what is that? Because this generator here actually is singular, so it has no inverse. Why is it singular? Well, for good physics reasons, because there is a stationary distribution and all that. So, you know, if you add with the generator on constants, it's 1. So it has a non-trivial kernel, so it's singular, it's not regular. So the inverse doesn't exist. Yet, hold on, let me write it as an inverse. So there are some mathematical points, but let me for the moment write it like an inverse 1 over L. Okay, we're almost there for equilibrium. So I say that the P lambda is minus L of U, and here is 1 over L. Okay, so what is it? In equilibrium, we just get minus minus, so I get, if I'm not mistaken, exactly U minus U. This is what I get in equilibrium. So in equilibrium, you get that the V is just the energy minus its equilibrium value. And what is then, what do you get here then for the heat capacity? Well, you have to take the temperature derivative. U doesn't depend on temperature, but I get minus U does depend on temperature. The minus and the minus cancel, so I get the derivative of the energy expectation value with respect to temperature. End of the story. I mean, it's not completely trivial, but it is at least consistent. I hope. Did you follow the equilibrium calculation? So the black is generally true. The black is nothing. The blue is an equilibrium simplification. So I repeat, in the blue, so the power is the rate of change. You look at, you're in condition X, you look at all possible transitions, and you look at the rate at which the heat is going in that transition. That's the rate, that's the heat. So you get the power, the expected power. Then you have to look at what is the power at time t, subtract the instantaneous value, integrate over time, that's the quasi-potential. In equilibrium, the quasi-potential is exactly equal to the energy. Okay, questions? Are there questions here, or it's hard to digest maybe immediately?
So how do you manage the similarity of L?
Okay, good. All right, so I was saying that L is singular, which is absolutely true. But how do you do that? Well, the point is that, you see, I have been subtracting the average. So it's singular, but it's kind of trivially to remedy it by subtracting the constant value. Because on the orthogonal space, eigenspace of the constants, it's not singular. So I have to take what is called a pseudo-inverse. It's sometimes called the Drazin inverse, if you have heard of that. But in fact, the definition of this Drazin or pseudo-inverse is exactly that one. That makes sense. Why? Because this difference is exponentially small in time. So this integral is converging. I have assumed, you know, in the very beginning of times, I have assumed that the Markov process or whatever process we have is exponentially fast to converge to its stationary distribution. So that's what I'm using here. And so this time integral is well defined, and it's equivalent to saying the inverse is well defined on that subspace. So that's not a big deal, but it's an important point. Thank you. So another main ingredient of last Tuesday is, of course, that I have to make, you know, between the mathematics and the physics, I have to make an important step. I mean, what does it mean? And that is happening here. This Q, which is the beta K over K, that's what I call heat, for good reasons. I mean, I was motivating more or less from the microcalorimeter also, right? So now, if we have a model that makes sense, where you can make sense of the heat, then we are in business. What we are going to do is, for models, we are going to compute Q, going to compute P, we are going to compute this integral, we are going to take this derivative, we are going to take the stationary distribution, and that's the heat capacity. Now you may wonder, is that feasible and is it worth the effort? So there are many questions and many studies that have to be done here, but that is somehow the structure. So let me add one more, and then I think formulas, main formulas are gone, but it's an important formula. So let me go back to this thing here. So remember the C lambda. Let me take this thing. Yeah. So an important remark, by the way, is that the average of V lambda in the stationary state is equal to 0. You can see that because if I take the expectation of that in the stationary state, well, it's of course the same as that one, so it cancels. So it's 0. So the average of V lambda is 0. That means that in fact, the excess heat, if I now write it in differential form, the quasi-static transformed excess heat is in fact equal to the sum is of course is a stationary stationary covariance between V lambda and something that you will allow me to call psi lambda, which is another letter, unfortunately, where psi lambda is the following thing. I just do partial integration in this integral using the fact that the average is 0 to obtain that the psi lambda is the derivative with respect of the nabla over lambda of the logarithm of rho lambda s. Actually, I'm not sure about the signs here, but more or less it should be okay, I hope. Do you understand what I'm doing or not? Maybe let me not be so fast here. Let me erase. Let me open this window here. So let me do it for temperature, just to make sure. So for temperature, we have the following. No? We have that the dq, the excess heat. If we just change the temperature, it's going to be what? It's going to be this expression here times dt. The minus sign, summation of x of the derivative with respect to temperature of v lambda x rho s lambda x. That's what it is. Right? So the heat capacity we see here up to a minus sign. This is the heat capacity. But now, if I look at that, I have, of course, that what is the rule again? I would like to change the integral. Yeah, so given the fact that the summation of v lambda x rho s lambda x is equal to 0, if I use that as input, then this I can write as dt summation over x, v lambda x, the derivative with respect to temperature of rho s lambda x. Right? By partial integration, we would say. Partial integration, I'm not even sure whether it's partial integration. It's just a Leibniz. Well, no, there's just nothing to do with partial integration, just the derivative of a product that we take. Yeah. Okay, so but that I can divide by rho s lambda and multiply with rho s lambda. And so here is the derivative of the logarithm. This is my derivative of the logarithm here. So in other words, let me erase the formulas and now let me go back to this. Let me emphasize that formula. Yes, please.
So the possible frequency is already subtracted with the steady value of the power. Okay.
Yes.
Okay. So you are moving through the parameter space in the lambda space.
But wait. V lambda is at fixed lambda, right? But Q lambda is not. Yeah.
Yes. So through the dividing the definition of the Q itself. Yes.
Here.
That's clear.
No, that's not the definition. That's the result.
So why do we need to take it average of the steady lambda?
That's the steady state average.
Yes.
By the way, I just want to make sure that you understand, this is not a definition, this is a result. The definition is here. So, and here I am doing exactly these excesses in the power at time t and instantaneously over a long stretch of time. So I'm going in my parameter space extremely small, but of course, there is always a deviation of order epsilon. And this difference is an excess in power that I have there, and I integrate it over a long stretch of time. And the result is that in the limit, I get something which is purely geometric, and is given in terms of the quasi-potential.
But my question is that for a given path,
Lambda path,
for a given lambda, but I always have the steady value of the power that is invisible.
Wait, for every lambda, you have a steady power. For every fixed lambda.
The transient part is coming from the transient.
Yeah, so this thing here is the steady thing, and that is the moving thing. Yes.
No? Okay. So if I for each value of the in between lambda final point, if I add the differences, that should also give me the Q. I mean,
that is the Q. That is the definition here.
Yes, that is so. Like I cannot relate in physically why the average.
Why this converges to that? Well, I'm happy you cannot.
That the average is coming there. I mean,
but it's not so strange that the average is appearing, no? It's not so strange. Because you're indeed in a quasi-static limit. So the only thing that you can hope for is to see the quasi-static averages. But now I'm moving in a geometric way over the curve.
Okay, but the V lambda is also by definition a state variable, right?
V lambda is this one, is a state variable. Yeah. So at every moment, for a fixed parameter value, I take a stationary average of this, how the V lambda is changing on the lambda. If I look at the rate of change of the quasi-potential in the quasi-static limit and integrate it over the trajectory, I get the excess heat. The intuition is not so bad, no. This V lambda is itself an excess for a fixed lambda due to the fact that I need time to relax. It's an excess in the sense that it looks at this one goes to that, but in the relaxation there is a difference. I take the full integral. That defines my V lambda, and then I change, and so that I have at every moment to look at. There's always this relaxation, and then I change a bit the lambda, and I integrate over all the possible over the trajectory. So it is a bit intuitive.
So is it similar to linear response in?
Of course, I'm doing linear response, but I'm doing it. Of course, it's linear response that I'm doing, but for thermal linear, for thermal, for example. But I'm not. So let me not elaborate too much on that issue. Okay, let me erase things. Is it okay? We will, in fact, only use in what follows. We will only use this algorithm. P lambda is this, and we will use this algorithm there. So let me erase.
No, Christian, I think the confusion you were finding V lambda, you have already taken the average. But
no, the V lambda I have not. It's a where is the x dependence? It's here.
I see. So that average is over.
So that average is not in the steady state, it's in the process. But for fixed lambda, where the initial condition is x, thank you. So this x means, okay, I should have said that this is x0. So I start in x, and I look at what is dissipating at time.
So last average is actually over x naught. I mean,
yes, this average is over x. Yes, thank you. I should have been more careful in my notation. Let me summarize all of this in its essence, so that we have an algorithm. I'm just motivating, these formulas just motivate in a way which unifies with equilibrium thermodynamics. It motivates the definition of heat capacity for non-equilibrium. erasing too much. So here is the summary of our algorithm. So step one will be this one. If you're giving me a model, say I'm doing it for a Markov jump process, and I suppose that I know what are my transition rates for my parameters lambda, then I take this ratio divided by beta, and I call it the heat because I believe that my model makes sense and it satisfies this local detail balance, so that I can really kind of without much embarrassment call it heat towards the thermal bath at inverse temperature beta. By the way, something is happening here that maybe you have not noticed, that here is a lambda and here I wrote an alpha. The point is that this is part of the assumption. Right? The alpha, remember, was it such that the lambda consists of a beta, which is the inverse temperatures, and all the other parameters. It's part of the condition of local detail balance that this is the heat, which is just depending on the other parameters, not on temperature. Okay, so I have the heat in this way. I define the P lambda in this way. And then I do the following. That's number 2. Find the quasi-potential, which is a function on my state space, on my non-equilibrium system, with average in the stationary state 0, for which, and I will now abbreviate the definition of this V lambda. It will be as follows, that the backward generator on the V lambda will be equal to so that's an equation for V lambda. So I have to find the function V lambda, so it has average 0. Average 0 is kind of in my convenience or my default, and it satisfies this set of linear equations. Do you recognize this set of linear equations? I wrote them here. I could not even erase them though. This is the same thing as I wrote here, because there I wrote V lambda is 1 over L lambda. The same thing. But now I have L lambda is just determined by my K lambda again. Maybe I can even write it out. So just to make sure, if I have a backward generator on a general function in X, by this I mean the sum over all y, kxy, fy minus fx. The notation is as follows. You look at how the function f is changing per unit time. So it changes by a jump from x to y at the rate kxy. That's LF of x. So here I do L of v must be equal to that power. By the way, just a remark, maybe you haven't noticed this, but if I take the average of P lambda in the stationary state, what is this? This is, of course, equal to the sum over x and y, k lambda xy, rho lambda stationary of x, times the logarithm of k lambda xy over k lambda yx. Sorry for again, and there is a 1 over beta in front or something. You see that? I just wrote, I plugged in all the formulas that I have. So it's stationary, so I have to take averages with rho lambda. And I plugged in the P lambda, so it is the K lambda and the Q lambda, I plugged in everything. So some of you may recognize here that this is always positive. That's an instance, if you wish, of the second law of thermodynamics. By convexity, this is always positive. I'm not going to prove it. So that's just the Joule heating, which is a positive. Okay, so that is, so I find that I have a model with a K. I can compute, well, both, and maybe I don't know, but maybe I have the stationary one. I can compute perhaps these things. I have my Q, and I solve this set of linear equations. And then what I do to get the heat capacity, so I get the heat capacity from the formula. I have two formulas for you. Either you do the derivative of this V lambda with respect to temperature in the stationary state with the minus sign. That's one thing you can do. But another insightful thing is that it is also equal to the covariance between the V lambda, this period, this thing denotes covariance, and okay, again I will be derivative with respect to temperature, the logarithm of rho lambda stationary. That's what we learned so far. So we have generalized equilibrium to non-equilibrium, and we have obtained a formula for the heat capacity as a covariance between the quasi-potential and the derivative of the pseudo-potential, if you forgive me, because this logarithm of rho, what is that? Well, again, before we say general things, let us again look at equilibrium. So in equilibrium, I repeat, in equilibrium, the V lambda is just equal to the potential minus its average in the stationary state. And the rho s is just 1 over the partition function e to the minus beta, the energy. It all goes well in the thermal canonical ensemble. So if I take this procedure, you let me not do it, but you can see that if I take the logarithm, I get something like beta u. I have to take the derivative with respect to temperature and so on and so on. You will get that this here, I hope, will up to some constants maybe be the covariance of the. This will be C lambda T in equilibrium will be the variance of the energy, right? So it will be proportional to u squared minus u squared. Variance of the energy. Because the pseudo potential here and the quasi potential are the same in essence. In non-equilibrium, that need not be true. This V lambda is directly related to heat by definition. It's the closures type potential. This thing is the Boltzmann potential because it gives you the occupation statistics. In terms of for people who like large deviation rates, if you are going from the microscopic to a kind of mesoscopic level, you get that this would be given in terms of the large deviation rate function corresponding to a Boltzmann functional. But okay. So the main point here is that you get this generalization from a variance of potentials to a covariance between pseudo and quasi-potential, and that makes that things get different. Things can be changing, and that's what we now want to understand. Well, to understand, we understand the formula somehow, but to learn how to see what we can get something of. So that stops like with the mathematical formulas, with the generalities. Is it digestible?
What is this osseous type of potential?
The quasi-potential,
No, osseous.
the pseudo.
Pseudo.
I mean, just words. I mean, just we need a bit of like a bit of fancy names. You know, this we call the quasi-potential. In equilibrium, it is just a potential. This we call the pseudo-potential. In equilibrium, it's just a potential.
I see. Quasi-potential.
It's quasi and pseudo. But now you see the interesting things that can happen is that. I should now start with the examples because I don't have much time. But one of the things that can happen is negative correlations. There can be anti-correlations between closures and the Boltzmann type ideas of heat, and that happens indeed for non-equilibrium heat capacities as one possibility, but still it's stable. While in the canonical ensemble, if you have negative heat capacities, you should worry no for equilibrium systems, but not. Okay, so that's that. So now let us do in like the last 15 minutes, maybe, if you allow me, some example maybe to make sure that we get it through, get it right. There is something important, of course, that why do you care? Why do you do all that? Well, I think I mentioned it more or less, is that the point of calorimetry, the point of thermal properties, is not so much that we like to have to heat our house, although it's important. The point is that you would like to learn something about what you don't know. You should think, though, that I do not know the rho is low. I do not know many things. Maybe I can only measure some things about the heat. And via that, I would like to understand, for example, something about that. So you should really inverse somehow the question. It's a matter of learning. Just like if people measure heat capacity, they discovered quantum mechanics in the beginning of the 20th century because they found out this below the kilo is not correct. Or there is this Schottky anomaly, means there is a two-level system somewhere. All these things. Okay, so now I have to think what model we are taking, but the simplest model that I always take is the quantum switch. Okay, I mean, in fact, there is more to say, be said here, but I cannot say anything. So here we have an example, which is the quantum switch or the two-level switch. I don't think I have been speaking about it, did I? So this is the case where we have a kind of two-level system where we are switching with rate alpha between these double well potentials. And so I am modeling that by my two-level system where I have always an energy difference epsilon between two levels, but I can somehow imagine two situations, namely that the 1 and the 0, one way of saying it is changing in the 0, 1. So if I am, say, in the minus state, maybe it is easy to go down, while in the plus state, for my levels, by plus state I mean this potential, then maybe it is easier to go from. It's easy to go from 0 to 1. So maybe to make sure that you understand me, we have a 4-state Markov process. And maybe instead of rushing through many examples, let me try to do it carefully with this example. Okay? So all the other examples are maybe more interesting, but at least we do one careful example. Let me try at least. So I have a 4-state Markov process. The states x are 1 minus, 1 plus, 0 plus, and 0 minus. Is that okay? So the states. And now I have to tell you the transition rates. So for example, from 1 to 0, I will do it with a minus. Well, it's not a good idea. I will put the minus here, because this I reserve for all kinds of parameters. So I have the minus to the 1 to 0. What did I say? The 1 to 0 is easy. So that is probably something like e to the plus beta epsilon over 2. And I put here a time 1 over tau, just to put the frequency together. Yeah, so you see, I have like 2 states in my system. I have a 2-level system, but usually, if you manufacture a 2-level system, it's not really a 2-level system, but at least in certain energy ranges, you can understand like a 2-level system. And a 2-level system, I call 1 and 0. And there is an energy difference of epsilon between the two. So that corresponds to the difference in energies here. But somebody is doing something strange with my system, namely it flips the wells to be the lower one and the higher one. So when I have this potential, I call it the minus, and if I have that potential, I call it the plus. So in that sense, I have 4 possibilities in my world. Right? And I just have transition rates. So the transition rates from 1 to 0. So I will a little bit go on. So that will be the same if I am in the plus state from 0 to 1. If I am in the minus state from 1 to 0, I have this 1 over tau e to the minus epsilon, which is equal to k. Maybe we should take a look. Oh, I have only one black. Ah, there. Yes. Oh, blue. Black. Oh, there is black. So this will be k plus 1, 0. And then the rate to go between plus and minus is just equal to alpha. That's my 4-state Markov jump process. Is it clear? People maybe even, I don't know. No, it's easy to convince you that if I look at my 4 states here, so maybe this is 1 plus, this is 1 minus, sorry, this is 0 plus, this is 0 minus, this is 1 minus, this is 0 minus, this is a 4-state Markov process, right? And it's easy to see that even though I have local detail balance, in the sense that the ratio of these two is just epsilon divided by temperature, I do not have global detail balance, but maybe that's an exercise. There is no global detail balance. So if the alpha is there, there is no global detail balance. In other words, if I go around and I look for the probability of a trajectory which goes this way or I go the other way, it's not the same. It's a non-equilibrium system. Okay, so now how do I compute the Q? So now I have the P. So the P, I will skip super or sub indexes. Now I will be a bit more sloppy. So I will have the Q, for example, 1, 0. The power to the top 1 plus. What is the power? Well, I have to look at where can I go from 1 plus. The only thing, so I have to look at is, okay, here is an important point. I can go from the 1 to the 0, right? If I go from the 1 to the 0, where is my scheme? With the plus, I have this thing. Right? So I write that this is equal to 1 over tau E minus beta epsilon over 2. And what is the heat that I am dissipating at that moment? It will be epsilon. Minus epsilon. Sorry. Is that clear? Right, so I always look at the heat times the rate. And I do this. So let me do one more. Let me do, for example, P0 minus. What will be the P0 minus? So I am in the 0. I go to 1.
It could go from 1 plus, it could also go to
1 minus.
1 minus.
Okay, so that I'm not taking. That's very, I didn't want to skip it, but it's very important. So here I am only looking at the transitions where I am doing heat, not the work. So I'm not going to write all the details here of the first law of thermodynamics, but that's what I'm using. So there's heat and there's work, and the heat is when you change the state. The other is doing work. So here the P0 minus, I go from 0 to plus in the minus state. So I get the 1 over tau, so it's the same, I'm afraid. And if I go from the 0 to the 1, the heat is also minus. So it's in fact the same. You can easily see, by the way, that there is a symmetry in this 4-state model. These corners will be equal in stationary. So it's in fact a hidden 2-level system, but non-equilibrium. It's a hidden 2-channel 2-level system. In fact, you will see a Schottky anomaly here also. Let's see the 2-level system. Okay, this I will not continue the thing, but that's how you get the power. And now for this model, of course, it's a four-state Markov process. And as I said, there is a symmetry, so it's really a two-level system. You easily find the stationary distribution. Unfortunately, I don't do it, but you can easily do it. And if I have, actually, maybe if you'd like to find it, I can give you a solution. I have this one there. Yes. So no, I'm not going to give you the stationary distribution. What I'm giving to you is the stationary power. So the stationary power, you mean that is this thing, no? The stationary power is here just alpha epsilon sinh beta epsilon over 2 divided by alpha tau plus cos beta epsilon. That's a stationary distribution. That's a Joule heating. Average Joule heat, and you can see, I hope at least, that is positive always. And non-zero, strictly positive from the moment alpha is not 0. It's a strictly positive Joule heating that you have. That's the dissipated power, the Joule heating for that system in its stationary state. So then you have the powers, you have the stationary, you take the subtraction, and you can find the V. The V I will not write down, but that's how you do it. I mean, the V, how do you find the V? You solve the linear equation, but you only have 4 states. So you can solve that system. In fact, there are only 2 states, so you can easily solve the system, and you get the station, and you get the heat capacity. And the heat capacity turns out to be, as a function of temperature, for tau fixed, meaning not depending on temperature, you get this heat capacity, which is magnificent magnification of the heat capacity at low temperature with respect to equilibrium. So this is the case of equilibrium. This is for an alpha non-zero. Of course, it depends on alpha, right? You can also compute, but that is what you see. So you see the Schottky anomaly. So you see, if you do that system, that you have underlying asymmetry of which is a 2-level system. Note that it goes to 0 at 0 temperature. This is an example of what we call an extended Nernst postulate. You know, the third law of thermodynamics in equilibrium says that heat capacity goes to 0. So here you also have it that it goes to 0. And you can, of course, I mean, here this, if you want to amuse yourself, you can compute everything, of course. You can also see how the heat capacity depends on the alpha and all that.
So limiting behavior near 0,
Yeah.
that also changes from equilibrium?
Yes, actually, very nice that you asked that question. So in equilibrium, this goes like exponential minus beta epsilon. In non-equilibrium, it goes e to the minus beta epsilon over 2. I mean, you can really see it in the way it goes to 0. Yes. I mean, for good reasons that I have no time to explain, but everything is explicit in these formulas, but there are reasons having to do with this covariance. But of course, these are already very special things for a specific model. So, yeah, I'm sorry I cannot have time, unfortunately, to get all the details, but let me add one more drawing to that, and that is that if the tau.
We started a bit late, so there's
Yes,
5
but
more
let me
minutes.
not rush too much. So if the tau is in fact presenting us with a barrier, which is this barrier here, which is like the Arrhenius type law for chemical reactions, you could say. If the tau is e beta delta, so it means that in our model you will have a kinetic barrier, right, which grows with low temperatures. Then you get a heat capacity, again the same drawing as a function of temperature, that has the more negative value, goes like that. Okay, I'm not sure anymore about my drawing, but the most important thing is, again, goes to 0, but it has a negative part at low temperature, from which you can find the kinetic barrier. So you can find the kinetic barrier. In equilibrium, there's no way you can find it. In equilibrium, the heat capacity does not depend on the kinetic barrier. It's always this thing, not independent of the kinetic barrier. But if you go to, so if you want to know the kinetic barrier of an equilibrium system, you go non-equilibrium, and you can find it via, well, maybe a bit of propaganda here for non-equilibrium, but you know, you get kinetic, dynamical information so that you can find by the negativity this kinetic barrier and its properties. But there are other features that I have no time to discuss here, but that is the general thing. It's not so much that you want to define something. The idea is that you hope it is useful for understanding properties of the non-equilibrium. And the point is, that is maybe the main point of everything. You forget everything if you wish, but here is the take-home message, is that the non-equilibrium heat capacity will not only give you information about the statics, which you may not know because it's non-equilibrium steady state, but the non-equilibrium heat capacity will relate it and will in that sense also give information about dynamics. And that dynamics is, even though this is a state function, is V lambda, because it's about relaxation, it's a kinetic equation you have to solve. And so it means that if you have, if suppose this is not going to zero, suppose there is no, that the Nernst postulate is violated, it will immediately tell us that there are states which kind of are not doing the right thing, where the relaxation in the heat properties is not joining with the main dissipative structure. These are words, but you can imagine that. The Nernst postulate now is not just the fact that this is getting non-degenerate at zero temperature. It's not only that. You also need a condition which is dynamical. And if it is not true, you get information. In fact, if it doesn't, what you need for it to be go to zero is that you have absence of like great localization phenomenon in your spreading of heat in the non-equilibrium system. So this is a bit vague, but that is the kind of thing where it leads to. Another thing which we have no information, we have not been able to explore is that if, I mean, you know, maybe or that in non-equilibrium there may also be phase transitions, not only zero temperature phase transitions, but finite temperature phase transitions. The theory of that is perhaps not so well developed as an equilibrium, right? What is a phase transition, how to characterize it, and so it's not so well developed. We would hope that perhaps the heat capacity would around critical, around phase transition, could also give information about what type of phase transition you can have. After all, one should not forget that thermal properties and heat capacities have played a role in the 20th century for understanding equilibrium systems. So that is a bit the purpose of that program, is to get this extra dynamical information from the non-equilibrium heat capacities. I think that I have said more than enough in the sense of a lot of vagueness and some formulas and some examples. But again, I'm here also this evening or tomorrow if you have some specific questions. Be very well. Thank you. You have a question.
So can you calculate the specific systems for which the rho is lambda can actually be calculated?
So we have actually the rho is lambda. That would give me another lecture series to talk to you about this rho as lambda. I can tell you some keywords here. So, for example, you may be interested in its low temperature behavior. I mean, to think that you can characterize the non-equilibrium steady state in general, like you have in the Gibbs formalism, is too much to ask. Because there's such a great variety of non-equilibrium systems, there is no single particular thermodynamics that would give you this lowest lambda. However, there are simplifying situations. So, if you're close to equilibrium, this is given by the so-called McLennan formula. It satisfies the principle of minimum entropy production. If you're at low temperature, very low temperature, the low temperature asymptotics you can do via a variation of what some of you know as Friedland-Wenzel theory, and you can get the low temperature asymptotics of that guy. Interestingly, it is of course not purely thermodynamic if it is non-equilibrium, but it has to do with the accessibility of X. So the probability of an X of a state is not just given by an energy or something, but it is also related to how accessible it is to get from other places. Others. I'm not sure whether you have been hearing about the Kirchhoff formula. You know the Kirchhoff formula? The Kirchhoff formula is a representation of the stationary distribution of a Markov process in terms of trees, graphical representations. You know that? It's easy to give you if you wish. I can give it to you. So suppose I have a Markov jump process and I'm using too much ink. So I have a graph, right? So think about like electrical network, but it doesn't matter. So I have a graph which is well connected. This is a graph. And I have every edge is like the transitions that I can have. So I have here maybe a state X and here a state Y, and I have correspondingly transition rates KXY. And now I'm asking, what is the stationary distribution in X? Kirchhoff already many years ago has been giving a formula for that. Amazingly, it's just because this is a linear, as I said, this is a linear equation. So you can use linear equation methods to find that. And this Kirchhoff formula is up to a normalization given by a weight. So there is a weight of this X, and this weight of X is the following. You sum over all spanning trees, and you take the product of the K ZZ primes, where ZZ prime is in the spanning tree going to X. So you know what a spanning tree is? So spanning tree is that it's a tree, it means some object without loops, but so that every vertex is visited. It's a spanning tree. For example, for this graph, a spanning tree could be like this. That's a spanning tree, for example. You see, I visited every vertex, but I made no loop. And there are, of course, many spanning trees. But now, if I want to know the probability of X, I sum over all the spanning trees, but I take the in trees, so they must be directed towards X. So I direct them via X, and I take just the product of the rates. That's the formula of Kirchhoff. So I know, if you wish, I know the stationary distribution as a graphical representation, except that this is useless. It's useless for two reasons. First of all, it's much too expensive for an algorithm to compute all the spanning trees. And secondly, it doesn't come with a kind of physics implementation. If we do physics, we'd like to understand stationary behavior in terms of physics. We know what is the unifying physics which is underlying. But at low temperature, this Kirchhoff formula you can get into kind of more physical nature, which is related to things that I have not been able to speak about, but which is accessibility and frenetic things. So that was your question. So what do I know about OS? So these kind of things. I think, I mean, many people have tried and wondered and hoped that there would be like a miracle formula for that one. There is one, but I mean, it's not, you don't want formulas, you want something which is useful. First comes the question and then comes the tool. But at low temperature, it's a useful formula.
Okay. You change alpha. Suppose alpha
Yes.
is non-zero, you increase it further.
Yes.
Then I would expect in this case that you have drawn tau is equal to the beta delta, I would expect only the positive peak to become sharper. But the negative peak should not change because it is giving me information about the equilibrium.
Yeah,
system.
actually, I have a plot here, and let me check whether what you're saying I understand. But in the point is that let me redraw it a little bit nicer, and let me tell you what is the truth. The truth is as follows. So I will draw two curves. So these are two curves, and this is going to lower alpha. So the lower alpha gives me here more negative and higher positive, and the higher alpha is this thing. This is for a specific epsilon, right?
Position, negative peak position remains same.
That's I do not remember, but everything is exactly calculated. No, it's not. No, it's not. It changes.
Then, okay. Then from this curve, how do you extract delta?
Because of course you know I mean I know the formula, no, for all of this. So I know how this behaves with delta. Because if delta is 0, you know, it depends on delta.
Yeah, but my only concern is delta is an equilibrium because it
Well,
is
it's a nice
it has got
value.
nothing to do with this
Absolutely.
flashing.
Yes. But so if I start to flash, I will see, because of the delta positive, I will see these things, and it will change with delta. So this is a curve for different alpha. What you really want is perhaps for fixed alpha, how it changes with delta.
I wanted to make sure that for a fixed delta, it doesn't change with alpha.
No, it does change. It does change. The curve changes with for a fixed delta. So can you say it again?
So for a fixed delta, if I just play with alpha, then maybe the peak position or whatever I'm using to extract delta, that should not be changed.
Actually, I know. I mean, I do know it, but not without looking at formulas. I guess what I wanted to say, there is information of delta in it.
Okay, anyway, there is a formula available.
There is a formula, right?
Another question is, you mentioned some cases where suppose this extended Nernst postulate doesn't remain valid.
Yeah.
So could it also be, for example, you are giving a mesoscopic description of the system.
Yes.
Maybe some energy is cascading down to some other length scale, other degrees of freedom, and you don't have any way
That could
to
be a cause of it. That could be a cause of it. I do not know the specific answer to that scenario, but that could be a cause of having certain mesoscopic states kind of getting isolated from the main dissipative structure. You know, what happens is that typically at very low temperature, the stationary distribution becomes concentrated in one state. But in the V lambda, you need to get there, that dominant state. So you could have situations where, for example, in a graph-like structure, I have here a merry-go-round where states are turning around, and then there is a long hair. But in fact, if I wait extremely long, everything will go to here. But because of this merry-go-round, you just spend too much time here, and that makes that this delay will make the certain quasi-potential explode and having not a good specific heat at 0 temperature. Or it can be that the dominant state is actually here in the dissipative structure, but that these states have to pass some barrier, which is kinetic or which has to do with interactions, so that you cannot go to the merry-go-round where the action is. That's the type of thing. So what you're saying is probably a possible reason for such delay that you have. There could be various reasons. The most interesting, personally, I find that it is caused by interaction. So that it's not something that you put by kinetic barriers, by hand also to speak, but that it's caused by, you know, like in a classic thing, like you have a jamming, but then for the heat that cannot go to join the action where the dissipation is really happening.
But you are saying that then if you wait long enough,
Yes.
in case, I mean,
so there is a unique stationary
distribution.
distribution. It has a unique stationary distribution, but it just has to wait too long if temperature goes to 0. Well, I wrote here 1 over tau already because the k is something in its frequency, right? It's like 1 over time, so that's already useful to write here the 1 over tau. But think about the transition between these two states, right? So you want to go with. It's not just the energy difference that may play a role, right? You also have to be hit hard enough to go over the mountain. That's what you need to do. But that's somehow the same thing if you go from here to here. It's kind of unsymmetric. So
This tau is somehow related to that RE
to the barrier, right? Yeah, to the barrier it is. Yeah. It's a kinetic barrier in the sense it's not like in the thermodynamics. I could also draw like that, no? The equilibrium doesn't care about that. The tau would change.
Another question is 1 plus, okay, you can go to 0 plus, but you cannot go to 1 minus.
So from 0 plus I can go to, what did I do? No, sorry, this is wrong. What I wrote here like this. From 0 plus, no, this is wrong. Sorry. So from 0 plus I can go to 0 minus, and from here I go to 1 minus. Was that the problem? I mean, this is the transitions with alpha. These are the alpha transitions in both directions. And these are the thermal transitions. And if you are plus, you are biased to go in this direction. And if you are minus, you are biased to go in this direction. That's why you see it's a non-equilibrium system, because you get a loop. But the point is that the alpha transition does not correspond to heat at the world. If we do the dissipative power, I'm only looking at the heat. Yes. 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 Yes, please.
So, I mean, if I understood correctly, but E tending to 0.
Yes.
So in equilibrium, the equilibrium state is actually governed by the minimum energy state.
Yes.
Right?
Yes.
Or
in non-equilibrium, not.
Yeah. So my question is that physically it is that when, I mean, so that's the essence of Nernst theorem. When T tending to 0, I mean, entropy actually vanishes.
Yeah.
So your thermodynamic state is governed by only the minimum energy configuration.
Yes.
So now, I mean, since it satisfies local digital balance, I don't see why that argument should not hold even in non-equilibrium. And in fact, the Nernst theorem holds. It says that, I mean, since it's governed by local digital balance, so I mean, it does not allow you to go to the higher energy state. So the minimum energy configuration of the macroscopic state, which is your non-equilibrium steady state, I guess.
But you see, in non-equilibrium steady state, you could have population inversion. So
but at T tending to 0, I mean, I don't see. I mean, within local detail balance, why
you can have local detail balance and population inversion. So it means that the occupation is really at low temperature in the high energy state.
So is it really possible?
It's just possible, yes.
Now, can you construct some example?
Of course I can.
Oh, I see.
I mean, of course, you have to play with some parameters to get it, and you have to invest work and all that. But that's why we use these things for all these works. We make refrigerators and all that. So to get another, it looks like ice, for example, even though it's at 30 degrees outside, because we have used work to make it ice. You know what I mean? I mean, you really have to make it non-equilibrium and work to pump the system up. And it may depend on the temperature, how much you have to pump it. That's true. You can pump it. It's not that at 0 temperature things become equilibrium. Not at all. I mean, right? You know, I mean, take these graphs. Suppose I have an external field that there is some bias. But the field is multiplied with beta. Because its local detail balance gives me, oh, it's gone. The local detail balance tells me that the rates is, so the rates is something like that, no? So I may have e to the beta and energy difference minus 1 multiplied with beta, but I can also have in this transition some field, some work that I'm doing to go from x to y, and there is again a beta in front. That's local detail balance. But also there is a beta.
No, but okay, local force, but that probably you did not consider here at least.
Local detail balance is okay.
No, that is okay, but force, the term you have written A. If I think at least it is not there in this
no, this is a QXY because the work is immediately, so it's really in F times the length maybe, no? Between the X and the Y. So this is the work done by an external force to take the particle from X to Y. So this is the instantaneous Joule heating divided by temperature, and its importance grows with beta large. Just like the same way as the energy growing. Why? Because this is exactly dissipated in the same environment. Does it make sense? They act in the same way. I mean, after all, suppose that without telling you, in fact, my force is conservative. So it's really not an energy that I secretly add. Then you cannot expect at low temperature that I go to the minimum of that hue. No, it's the minimum of the sun. So you see how even in equilibrium, if secretly I have added energy, of course, if you change it, no, it's another energy. So you change the landscape, so you will not keep going with the same hue. So that makes it more exciting. Low temperature non-equilibrium physics.
Another one, maybe?
Yeah.
I think you talked about phase transition.
Yeah.
So, I mean, what kind of information you can extract just looking at the heat capacity? For example, I mean, now equilibrium phase transition. I mean,
Yes.
you know that there is latent heat, so you know this is a first order kind of transition. Specifically divergent, it's second order. So now, immediately, if you take a model and say KLS model, so Ising model, you know that this happens. Well, some sort of.
Yes. Yes.
So then you drive with a field.
Yes.
So do you think that CT will have some?
I hope so. I don't know.
But you
But I
can,
hope so that there would be change or I don't know a sign. We don't, at least as far as I do not know a good phase transition theory for non-equilibrium. I do not know how the phase diagram is truly changed in a kind of general way if you add non-equilibrium. If I add thermal properties, maybe we will know a little bit more. I don't know. It's a program for the future. So next time I come, I will try to give you an answer, but not know. I just don't know. I only know something about non-equilibrium phase transition at zero temperature, which is because of the forces there at zero temperature. By the way, the main reason I don't know is, of course, that if I have to do this in phase transitions, it will not be with 4 states, right? I will do it with, I don't know, 2 to the 10 or so states, or 2 to the 100 states, and this linear programming thing will be a bit difficult. But okay, there may be ways to do it, but we have to figure out what is the reliable way to do that, including lattice gases. It's a bit like a computational problem. There's no problem. The interpretation of all of these things is easy, but there is a serious computational problem to go to solve linear equations of 2 to the 100 matrices. By the way, there is something that helps here. We can solve this using the matrix Forest theorem. This is called the matrix tree theorem for people who have seen that. Kirchhoff formula is like the matrix tree theorem, but that is like a homogeneous equation. But if you have a source term, that's called the matrix Forest theorem. So there's also a graphical representation for that, but that doesn't help you for very big systems. Okay. So far, so good. I hope it was useful. Thanks a lot for being here. It's also for always, I mean, maybe you know that already, that if you want to understand something, the best thing is to teach it. So I'm happy I can teach it a bit so that I understand a little bit better. Thank you.
Absolutely.